afternoon, or I don't know, good day, good lunch. Can you say that? Anyway, hi and welcome. I'm Madde, and you are watching 1337's Wednesday Knowledge Stream. So, Wednesday Knowledge Stream, does this thing have a name now? Well, yes, it does. It's Wednesday, it's knowledge, and it's a stream. It's easy, right? So, we love sharing knowledge with you, and that's what we love to do, and we do it best. So, we are here, we are sharing knowledge, and we do it remote because as many of you are sitting at home in social distancing, and so am I. So it's a great opportunity to reach out to you. And if you have any ideas for topics that you want to hear more about, or maybe you know this speaker that you would be super interested to hear speak at a session, don't hesitate to reach out. Write to us in the chat, write a comment, or send an email, and we would be very happy to look into it and see if we can get that person here. So, don't you just love hearing good story? You know, when you get to hear a real-life example of a team that had a certain problem that they tried to solve, or they had some technology that they wanted to try out. I mean, I think that's the most fun way to learn and hear more about the new technology. And that's exactly what we're going to hear more today about. So we are invited to hear the journey of a team who went from being like, oh, what is a tenant, to a full multi-tenant solution. And the master storyteller we have with us today is my dear colleague from 1337, Helen Toomik. So, hi, Helen.
Hi, Madde.
Hi, how are you?
I'm good, thank you. All good here in the sunshine.
Oh, it's sunshine here in Skåne as well. It makes me very happy.
Makes a big difference.
It really does. I mean, imagine if we were in isolation in the middle of November, it would be horrible. So, yeah, we gotta enjoy the small things, right? So, I just want to wish you very welcome to this stream. I want the audience to get to know you a little bit better. So what we've done with the other speakers before is that we've played a little game called Two Truths and a Lie. So I was wondering if you would like to share with me also two true things about yourself and one false thing. And then we can go ahead after your session and discover which one was the lie.
Okay. So this is going to be the bragging edition of this game. I'm going to
I like that.
Making 3 extravagant claims about myself, and curious to see how many people pick up the lie. So 3 things. I have climbed the Kilimanjaro. I have eaten grilled kangaroo meat. And I have met the King of Sweden.
Oh, wow. Well, they all sounded very interesting. I will think about this for a while.
2 of these are true, for real.
Okay, interesting. Well, as usually, if you in the audience have any questions for Helen, please post them in the chat and I will forward them to her after the session. But I say let's get started, and I'll hand over the word to you, Helen.
All right, thank you very much. Let's see if I get my presentation going here. Right, let's jump right in. The title of my talk is Fumbling Towards Multi-Tenancy. And this is basically the story of our team's journey towards multi-tenancy. About a year ago, my team was asked to take an application from what's a tenant, from no concept of tenancy at all, to a full multi-tenant solution where we could have multiple customers sharing the same application. And today I'll be sharing the story of that project with you, telling you from beginning to end how we thought about this, how we approached the problem, and where we ended up. First, a brief introduction to the application. This application is for mobile phone insurance to customers of a phone operator. So the end user, that could be you, you buy a phone from your operator, and maybe you also buy insurance for your shiny new phone from the same operator. And if your phone operator has purchased the service from us, then you use this application that I will be talking about if you happen to damage your phone and need to make an insurance claim. Plus the application takes care of all the stuff that needs to happen in the background to actually make sure you get a new phone to replace your broken one. So even though the customers of the application are mobile phone operators, they don't ever use or even access the application. They just buy the service on behalf of their end users, you guys owning your phones and breaking them. It's a web application. It's built on .NET Core, Entity Framework Core, and it's hosted in Azure. So while the architecture areas of this talk are going to be technology agnostic, when we get further down into implementation details, .NET Core and Entity Framework Core is going to be the basis for those examples. And this application then, built for providing mobile phone insurance, was built for one specific phone operator based on their demands and their requirements. And it was running and it was working and it was great and customers were happy. And our business people were so happy that they realized this is good stuff. We could sell this to more phone operators to make more money. Unfortunately, the application was in no way prepared for that. There was just no concept of having multiple customers or tenants or anything. So we needed to really start from scratch here, start thinking about how can we introduce new customers to this, in a sense, kind of stupid application that doesn't know anything about customers. And how can we keep their data apart? How can we ensure that one customer's data never mixes with another customer's data and never crosses that tenant boundary? So what we needed here was multi-tenancy. And that's what I'm going to talk about today. The plan here is kind of a pyramid-shaped approach to our story, and a pyramid in the sense that we start an inverted pyramid, actually. We start with a sort of high-level, broad strokes. How do we think about multi-tenant application architecture? And then we're gradually going to go further down and into smaller and smaller details, from application architecture into database architecture, then into actually implementing that database architecture. And then finally, how can we add per tenant business logic to our application? So we start at the top and then go into more and more detail. So the first parts are going to be the technology agnostic parts, and the final details are really, we're in deep in .NET and Entity Framework Core. What's the first thing you do when you start working on something new and you have no idea how to do it? You go and ask experts, right? So that's what I did. I went off and I Googled for days. I read blog posts, I read Stack Overflow questions, I read Microsoft's documentation. I asked lots of people here internally at 1337 to get advice on how they would approach this kind of problem and how have other people solved this problem, because it's not a new problem. It's not unique to us in any way. And when I asked these experts in person or on the internet, the kind of answer that I got was often like this: this is what we did, and you should definitely do the same. This talk is going to be different. I am not an expert. I don't claim to be an expert at all on multi-tenancy because I've only done this once. I've done this one journey from no tenants to multi-tenancy. So I'm not going to tell you what you should do. I will tell you what we did, and I will explain to you why we made the choices we made. And our choices may not be right for you. I am very convinced that in many situations, our choices would be wrong for you. And I can even imagine differences in our own situation that would have forced us to make very different choices. But I'll tell you what we did and why. And currently, at least, we haven't regretted any of our architecture choices. So I think, at least for our situation, the choices were good. And if you are in a similar situation, then our choices might at least help guide you. When it comes to implementation details, though, we actually ended up making two course changes because we ended up in dead ends. We saw a technology or a solution that seemed great, seemed like an excellent fit for our problem, and we implemented it and got almost all the way there and then realized that the last little bit just won't work. So that's also something I'll be explaining and describing in more detail. Before we dive into the architecture, it's worth thinking about what multi actually means. How many is multi when we talk about multi-tenancy? I've heard that in some pre-literate cultures, the only counting words they have is one, two, and many, and that's enough because they don't need to do advanced maths. If it's more than two, then it's many. In the coding world, a more useful scale is 0, 1, and many. If you have none of a thing in your application, then you don't need to think about it. If you have 1, then you have a variable of some kind to hold it. And if you have many, then you have a collection of some kind to hold these things, objects, items. You have a list or an array or a database table or something in that vein. And that's enough when you're coding, but multi-tenancy is not just about coding, but about architecture. And when you're thinking architecture, you need to raise your thinking one step further, and you need to take into account things such as infrastructure and performance. And when you start thinking in those terms, it can be helpful to differentiate between many and very many. If it's many, then you can keep things in your list or in your database table. If they're very many, then your list might grow larger than the available memory on your server, and then you need to think about it differently. You need to find solutions for handling very many things. In our case, we're talking about mobile phone operators, tenants, number of tenants, and in reality, they will be many, or you could even call it few, and they will never be very many. You will be able to count the number of possible tenants in our application on the fingers of your hands, and maybe you take your toes to help, but we will never have thousands or millions of tenants because it's not that kind of application. If you were Facebook, things would be different. Then we'd have to architect it for the very many scenario. But in our case, many is enough, and that's what we need to take into account. That's what we need to scale our architecture for and our design. With that said, let's move on. Let's first dive into the high-level architecture question. And the first question to answer, the first question that I realized I had to find a solution to was whether we wanted a multi-tenancy solution or a multi-instance solution. What does that mean? There's no real physical world equivalent that you can use to get a grip on this difference, because in the physical world, you can't share resources the same way as you can in the digital world. But just to have some kind of, sorry, wrong page. Just to have some kind of example for you. Think about a shared apartment. You have roommates, you each have your own rooms, but you also have shared rooms. And the kitchen in a shared apartment is what you can think of as a multi-tenant resource. The kitchen is shared, you all use it. There are rules in place to make sure you don't collide when several people want to make breakfast at the same time. And if you make any upgrades to the kitchen, it benefits all the users, all the roommates in this apartment. For an example of a multi-instance resource in your apartment, think of your bedroom. Your bedroom is yours only. There is no sharing except with people whom you explicitly invite into your bedroom. Otherwise, it's yours, and every roommate has their own instance of a bedroom. And for me, when I approached this question, when I was met by this and started thinking about it, multi-tenancy seemed like the obvious solution for a cloud application, because that's the kind of solution that you encounter in almost all the applications that you use. We're all in the same Facebook, we're all in the same Twitter, we're all in the same, whatever shopping application you use. It is all multi-tenant. But multi-instance is still very much a valid choice, especially now with modern solutions like containerization, automation, and it has clear advantages. And a lot of these experts whose advice I read were recommending multi-instance, because the multi-instance solution clearly gives you stronger tenant isolation. Tenant isolation is obviously the ultimate goal of a multi-tenant or multi-instance or multi-tenant architecture, because that's kind of the whole reason why we're doing this. One tenant should never ever be able to access or change the data of another customer or another tenant. And the strongest way, the most solid, the safest way to achieve this is to go multi-instance. Because if you have literally one customer's data in this instance and another customer's data in this instance over there, possibly even on separate physical servers, there's no way that data can accidentally leak. You'd have to make a real effort to make data leak from a server over here to a server over there. So that's like, in a way, the gold standard. You can't get a stronger tenant isolation than you get with a multi-instance architecture. But of course, no benefits come without costs. And clearly the cost of a multi-instance architecture is going to be higher in the long term. In our case, very obviously, we have our application hosted in Azure. So we have all these resources in Azure that we pay for per resource. And if we, instead of one instance of the application, suddenly have two instances of the application, we will have two of everything in Azure. So we would be duplicating all our resources, and all of them cost money. So our hosting costs in Azure would double overnight. Still, hosting costs are not the sort of majority of the costs of keeping this application up and running. It's a small part. And our judgment was here that it's worth paying this cost to get that strong tenant isolation, to have the separate instances with data clearly separated. And a few Azure instances don't cost that much. So we started designing, we started breaking down this architecture. How would we actually do this? What would we need to change in all the different parts of our application, in all the different layers? And pretty soon we realized that the cost is higher, not only in the long term, but also the upfront development cost for a multi-instance solution would, in our case, be significantly higher. As I said, multi-instance is nice if you have automation, if you have your application in a container that you can easily deploy to over here and over there and over in that third place as well. But we had none of that. Our application was really not built with this kind of situation in mind. It was just this one app service in Azure. So we would need to develop or buy and configure all sorts of tooling. We would need tooling for deploying all these instances, for managing and monitoring all of them, for centralizing logging and keeping, at the same time, keeping track of which logs come from which tenant's instance. We would need to develop some kind of solution for our administrators and business analysts to query data across all these instances, because they do data analysis and they, of course, want to sort of get a picture of the data as a whole and not just all these little pieces about one tenant here and one tenant there. And at this point, we were kind of starting to wonder whether the cost would still be worth it. And our conclusion was that yes, the cost is higher, but the cost is worth paying. We still want that strong isolation that we get from a multi-instance architecture. So we continued our design thinking. We continued breaking down this vague plan into doable, actionable steps. And as we were doing this, we realized that some of the application details in our specific case would be really hard to implement in a multi-instance solution. More specifically, we have integrations. Most applications probably have integrations. And in our case, we have integrations not just outgoing when our application makes requests to third-party systems, but we also have incoming requests from third-party systems into our API. And they, of course, couldn't care less about our tenants and instances and whatever architecture we come up with. They just want to make an API request and they want us to handle it. And that works very nicely today in this single tenant or no tenant world. But if we add multiple instances, we somehow need to make sure that the incoming API requests end up in the correct instance. So we need to actually add another application in front of our current API that would service these requests and proxy them to the right instance. And at this point, I was looking at a list pretty much like this. This big, bold benefit of multi-instance, and all these costs adding up, all these costs that really kind of are pushing us in the other direction, and things that would be a lot easier and cheaper if we went down the multi-tenancy route instead. And as I was looking at this list, it struck me that what I was doing here was something that I, in my head, described as fear-driven design. I was letting this one requirement of strong tenant isolation overpower all other arguments. Isolation, 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 and wasn't really properly weighing this against the costs anymore. And I shouldn't let the fear of what if we get tenant isolation wrong? What if we don't get this right? I shouldn't let that fear guide all of my design and my architecture. There are other ways of achieving strong tenant isolation in a multi-tenant solution or architecture. We can achieve this by being really careful about how we implement this solution. We can be really careful about code reviews, unit tests, integration tests, acceptance tests. There are lots of things we can do to mitigate the risk of leaking data between tenants. We don't have to go down the multi-instance route just because it's the safest and strongest one. So that's what we did. Multi-tenancy, given all these arguments pushing us towards multi-tenancy, is the route that we finally ended up choosing. And this was actually after we'd invested quite a lot of work. We'd done all the design in quite a lot of detail and actually started prototyping some of the steps for the multi-instance solution. And in a way, it felt like a waste because I'd literally spent, I don't know, weeks on this. But at the same time, this investment in doing the detailed design and actually starting to prototype things, that's what helped me discover just how much the cost would be of the multi-instance route. That's when I discovered that we were going to need all these deployment and monitoring tools, and we're going to need to think about those incoming third-party API requests. And I wouldn't have discovered any of that if I had just done a high-level sort of architecture discussion, even with experts or other team members to act as sort of to give me advice and discuss things with. The only way to discover the right solution for us was to do all this somewhat costly design work and look at all these nitty-gritty details. Phew! At this point, the hardest part was done. The hardest, the most expensive decision was done, and we could move on. So let's move on in the story. Let's move on to the next layer down. So from overall application architecture, moving down to database architecture. What are our options? At a high level, we have 3 options here to choose from, based again on all sorts of reading and articles that I found on the internet. Maybe there's more, but these are the 3 that I found and condensed all my knowledge into. And the first option is having a database per tenant, which is kind of like the the multi-instance architecture, but in the database layer. The second option is to have a shared database, but with separate schemas per tenant. And then the third option here is to have a shared database with tenant ID columns in the relevant tables to keep data tied to a specific tenant, to keep the data apart. So you can see this really mirrors the choices we had for application architecture. We have the multi-instance, i.e. database per tenant solution, and we have the multi-tenant, i.e. shared database solution. And let's look at these in a bit more detail. And as we do this, you're going to discover that these all have similar benefits and costs as we had in the application architecture layer. So database per tenant, just like a multi-instance architecture, it gives you strong isolation. It also gives you more flexibility and more power to customize things than the later options that we're going to look at. But because the isolation, the separation is so strong, it's difficult to share things. It's difficult to run queries across tenants. It's difficult to, or at least more difficult to work with deployments and migrations. If, for example, you have several tenants and each one has a separate database, and you deploy the same new version of code to all of these, and your deployment includes some database migrations, maybe the migration works in some of your instances but fails in one of them. Suddenly you have multiple databases that are out of sync with each other when it comes to schema and when it comes to database structure. This is something you need to be able to handle, to pick up, to notice, and to be able to handle if you have a multi-instance solution. And again, last but not least, the cost is higher. If you're in a hosted solution like we have in Azure, having a database per tenant means that your costs for your databases are going to scale linearly with the number of tenants. Double your number of tenants, double the cost of your database servers. Specifically, the cost issue, you can solve by doing a slightly cheaper version of a database per tenant, which is a schema per tenant. And this is in all other aspects just like the first option, but it's cheaper because you only pay for one database server and you separate the different tenants' data by schema instead. Otherwise, it's all the same, so there's really not much interesting that I can say about this one. So let's move on. The third approach here is having a tenant ID column to separate data for different tenants, so you can keep track of what data belongs to what customer, what tenant. And the costs and benefits are here just a mirror image of what we had in the first option. So the things we had as pluses there comes up as minuses here, and vice versa. So the two obvious minuses are you get weaker tenant isolation. There's more risk of sort of getting your wires crossed and leaking data, and it gives you less flexibility. On the other hand, it's cheaper and it is simpler and easier in all the aspects, all the dimensions that we could think of that were relevant for us. And when we looked at this list, even one of the minuses, even the point that says that this is less flexible, isn't much of a minus in our case, because we don't need flexibility. And in a way, we don't even want flexibility. What kind of flexibility could you get with if you had separate databases per tenant? You could, for example, allow different performance, or beef up one customer's database server while keeping another one smaller, which is great if you have customers of wildly different sizes. If you have one giant customer and then 1,000 small customers who are hundreds of times smaller in terms of amounts of data, then maybe you need to assign more resources to the large customers database, because if they're all in the same database, the large customers' expensive queries might mean that the smaller ones experience bad performance. But in our case, this is not relevant. The mobile phone operators are going to be roughly of the same size. It's not like a blue whale versus a minnow case. It's not going to happen. We also don't need to allow our customers to upgrade the databases at different paces. We don't expect them to ever need customer-specific database restores. If you have customers who have access to their own data in their own database, then one of them might mess up their database, and then they might ask you if you can restore their database. And that's, of course, only possible if you have separate databases per tenant, because if you restore your one and only database, then you'd be rolling back data for all the other customers as well. But in our case, our customers, the mobile phone operators, they don't even know our database exists. They don't touch it. They don't have any access to it at all. So there's no opportunity for them to do anything in the database, and therefore no reason for us to restore data for one customer, but not another. Which means that really half of those minuses on this list go away, and we're left with lots of pluses and just one minus. And as you can probably guess where this is going, this is the option we ended up choosing. Not only because of pluses and minuses, but also because it fit the overall path that we were on. We had chosen in the overall application architecture to go down the multi-tenancy route, and this is a natural, logical next step in on that path. So we're on the sharing path. Let's keep going down the sharing path, and let's go all in, and let's share everything and make sure that we get our implementation right, so that no data ends up in the wrong place. That's the architecture part done then. At this point, we have our application architecture, and we have a plan for the database architecture. And the next important piece of the puzzle is, of course, how do we implement this so that we get that strong tenant isolation, so that we don't accidentally leak data? Let's look at that. The goals here, as I thought about this, the goal needs to be that the multi-tenancy architecture is there, and it just works. And most of the time, developers shouldn't notice it, and should definitely not need to think about it. They shouldn't need to remember, oh, when I'm adding this new feature, I have to remember to get the multi-tenancy bit in there, because otherwise I'll mess things up. That should never be necessary. The key to building something that is future-proof and robust and solid is to make sure that you don't build it on the assumption that people will have to remember to do things right. The system should remember to do things right, and people, developers, should be able to just code and assume that the system is there to support them. Think of it as the foundation of your house. It's there. You don't need to think about where do you put your foot when you're walking. Does the foundations really support you here, or do I need to remember to step in the right place? You never do that. And the application here should be the same way. The multi-tenancy implementation should support the whole application and all the coding that you do without you having to remember to get things right. The right thing should happen automatically, always, without you having to make an effort. Let's look at the implementation then. The goal, or the sort of where we want to end up with this implementation, is that we always need to know the current tenant. We need to know for every user, for every request that is made, which tenant are we working with. And we need to get that information all the way from where the request hits the application, all the way down to the database layer where the actual database queries happen, which is where we actually need to achieve this isolation. Because it does need to happen at the very lowest level possible, rather than up in the UI or up in any kind of business logic layer. So we need to get that information. We need to get the tenant information in a reliable, super reliable way, all the way to the database queries. This being a web application, it's all about requests. And what we did is, as soon as a request comes in, we look up what is the tenant for this request, and we store it in the user session. We have two kinds of users. We have you, the end user, who broke your phone because you kicked it because you were angry and now you need a new one. We have you making your insurance claim. And when you arrive in our web application to make that claim, we get your tenant information from the URI of the endpoint at which you arrive. So we have the operator name in the URL. We pick that up and we store it in the session. And for the adjusters and administrators who work with your insurance claim, approve it, make sure you get a new phone, they get a choice when they log in. So as soon as they log into the application, there's a drop down and they pick from tenant 1, tenant 2. And when that choice is made, again, we store it in the session. So whichever group of users you're in, whichever way you come into the application, the moment you arrive, we know which tenant you belong to, or in the case of adjusters, which tenant you're currently choosing to work with. Next step, we need to get that tenant information from the web layer down into the API layer. And we do that with request headers. Every API request gets a header with tenant ID in it. All the requests go via a centralized request broker. So whatever component in our web application wants to make a request to the API, they go through that centralized request broker, which automatically picks up the tenant ID from the session and attaches it as a header to your API request. Once that request then hits the API layer, there's a piece of middleware in place that automatically looks up the tenant ID header and sets it on the DB context, which is the class and entity framework that sort of specifies the context for your database operations. And this is request specific. So whenever a new request arrives, a new DB context is created. And in this case, immediately attached to or tagged with your current tenant. So again, as soon as something is created, we know which tenant it belongs to. And at this point, we have tenant information where we need it because the DB context is where the database queries will happen. So next step, we will look at how to actually implement tenant isolation in the DB context and in all our database queries, again, in a reliable way that just happens automatically. So let's look at that. We're diving into actual code now. These are, for the most part, screenshots from our actual code. In some cases, I've had to anonymize, remove some names of tenants, remove the name of the application. But this is actual code. This is not made up examples. Tenant isolation has two sides. When you come this far down in the details, you have to make sure that users cannot see data that belongs to another tenant, and you have to make sure that they cannot change data for another tenant. And we're going to look at both of these parts one at a time and start with data reading. If you're using Entity Framework Core, I'm not sure about earlier versions of Entity Framework, but at least in Core, it turns out you can get this pretty much for free because Entity Framework Core has a built-in feature called Global Query Filters. It's a built-in feature, no extra sort of packages to download or anything. You can just write a few lines of code and you've got it. So here we have an example. I have this insurance entity. And to mark it as tenant-specific, we've made it implement an interface called Tenant Entity. And we do that for all entities that are per tenant. Not all entities are. We have, for example, a list of countries in our database, and the countries of the world are the same for all tenants, regardless of any wishes or desires. So some of our entities are not tagged with Tenant Entity, but the ones that belong to specific tenants, such as insurance policies, they are tagged with Tenant Entity, and that means they get a tenant property. And then in that DB context class that I've already mentioned in Entity Framework Core, we configure the DB context to apply a query filter for all these entities. So what this code here is saying is whenever we're working with insurance entities, apply this query filter that looks at tenant ID of this entity and only returns it if the tenant ID matches this .tenant ID. And this being the DB context means if the tenant ID of the entity matches the current tenant ID that we're working with. And it's literally just that. These 4 lines of code, plus adding the tenant property to the insurance entity, means that anytime we have a database query that is trying to fetch insurance entities from the database, this query filter is automatically applied, and you will only ever be able to retrieve lines or rows from the database where the tenant ID matches, automatically with no extra work, regardless of the kind of query that you write. So that's safe database reads solved in about 10 minutes of work. Let's move on to the writes. Let's look at what we can do to make sure that you as a user, or you as the application maybe, can never change another tenant's data. Again, we're in the DB context class, the same entity framework class. And here we are overriding the save changes method. I've left out the method signature because I couldn't fit it into my presentation here, into my screenshot. But this is what we have in our save changes method overriding the base DB context class. What happens here is basically we kindly ask entity framework to tell us, to provide us with a list of all changed entities, all entities that we are about to save if we go ahead with this. And we get from these entities, from all of them, we get the tenant ID. And then we condense this into a list of distinct tenant IDs and look at what tenant IDs do we have, what tenants are we trying to save data for. The first check we have is simply counting the number of distinct tenant IDs. If the count is more than 1, then obviously we're trying to save data into more than 1 tenant. And since we don't allow saving data across tenants, this is a clear sign that something has gone wrong. We throw an exception and we don't allow the save to proceed. We don't allow this data to be saved because it violates our assumption. The next check just looks at the first or the single tenant in our list. We passed the first check, we know that we will only have 1 tenant ID. And here we just double check that the tenant ID that we are saving data into matches the tenant ID that our current tenant ID, the tenant ID of this DB context. And if we are supposed to be working with tenant 1, but we're trying to save data for tenant 2, then again, somehow something has gone wrong. This is not allowed. We throw an exception and we don't let the data to be saved. Again, this is what 15 lines of code, and here you don't even need to do it per entity type. This is just these 15 lines of code, and that's it. We have defensive saving in place. We have code here that will not allow you to save data from one tenant to another. We did actually add one more layer, even though we now have both safe reads and safe writes. We added another layer of safety for database reads. And this is built upon row-level security, which is a built-in feature in Microsoft SQL Server. So if you're using SQL Server, you get this, again, built in, probably not in all versions, but in all modern versions, this is present. And this has 2 components. The first screenshot here, the smaller one, comes from, again, the DB context class. And the second screenshot is from a database script. So the second part lives in the database itself. And this is kind of a repetition, but in a different layer of the same logic we had before. We set in this first screenshot, whenever as soon as a database connection is created, we set a session variable. We set tenant ID on this database connection. We basically tie this connection to our current tenant. And in the second screenshot, we use this session variable. The second screenshot has 2 parts. The first one is a function that you create in the database that simply compares the tenant ID parameter to the tenant ID variable in the session and returns 1 if they match, and it returns 0 if they don't match. And then the third bit here is the one that ties them all together. what we did was create a security policy for each tenant-specific table. And the security policy simply applies that function to all queries working with that table. So it's like the query filter in EF Core, but this is in the database layer. When querying here the claims table, do return the rows where the tenant ID matches what's in the session. Do not return the rows where the tenant ID doesn't match. So this adds another layer of security for database reads. You might be wondering at this point, why are we doing it twice? Why do we not trust our first solution? Yes, we do. We very much trust the first solution. But the thing here is that these two layers of security or tenant isolation for database reads, on its own, neither of them covers all cases, all use cases. The query filter is needed for unit tests, because if we just had the role-level security in the database, all our unit tests would be without any knowledge of tenants, because the unit tests don't use the actual database. And you can't have role-level security in mock or fake databases generally. The role-level security, on the other hand, is needed for third-party database access. We have those business people running reports, and we have actually a few other applications that read data from our database. And we wanted those applications and those analysis tools to get the same kind of isolation that our own application has. So we added role-level security to cater for these use cases that access the database outside of our own application. Turns out, though, that the performance of role-level security really sucks. There's no other word for it. We had queries that took 3 times longer with role-level security. So in the end, we unfortunately had to turn it off for some of the larger and more larger tables with more costly queries, because it just wasn't acceptable performance. And we were quite happy then, but we also had the query filter in place, because that was really our main solution for this. And the role-level security was kind of an extra belts and braces solution. We wish we could have used role-level security all the way, but something needs to be done before, on the Microsoft side, something needs to happen to performance before we can actually use this for real in production. So where are we now? We have our architecture in place, mapped out. We know what to do. We have our implementation of tenant isolation in place. We now have tenant isolation for both database reads and database writes. We effectively have a multi-tenant application. We could let all these tenants in and they could start working and no data would be leaking. But of course, in reality, we were not quite done yet, because business logic. Of course, we would want all our different tenants, both our different tenants in this case, to use exactly the same application logic. We would want them to have exactly the same requirements and expectations, but they don't. At the very least, they want the application to be styled to match their own websites and applications. So if you're arriving from tenant 1 in this insurance application, you should feel at home. You should feel that this matches the styling of the phone operator's own website. And if you're coming from tenant 2, then you want the styling to match their styling. So we need to make adjustments. We need to make our business logic customizable per tenant as well. What is the simplest way to adjust things, to make different choices for different scenarios? It's an if statement, right? So that might be your first idea of how to adjust business logic to different tenants. This is not a very opinionated presentation. This is a story, but I'm going to have a very firm and very firm opinion here. An if statement is never the right solution for per tenant logic. And that's because it leaves gaps that you're only going to discover by accident when you add new tenants. So don't do this. Don't use if statements to customize your business logic. At the very least, use a switch statement instead, because what that does is it gives you that safety of a default case where you can throw in an exception if you encounter this code with an unknown third, fourth, fifth tenant. In the if statement case, you just silently fall back to doing nothing, or silently fall back to the else case, and you might well end up with bugs that you don't discover at all. In the switch solution, you'll find out very loudly that you have missed a case here. And a switch statement is simple, and it might look too simplistic, but it's perfectly enough for the simpler decisions in your application. For example, the style sheet. You have two tenants, and one wants a blue page and the other one wants a red page. A switch statement is perfectly enough to give you the right CSS file for the right tenant. But for larger pieces of logic, where you actually have to make calculations, go down different routes through your logic, you're going to be needing something more than that. And what we use is the strategy pattern. We're going to look at examples in just a few moments. But I wanted to also describe an option that we decided not to use. And the discussion here goes back to the difference between many and very many. Many tenants, a handful of tenants versus thousands of tenants. The strategy pattern still means that your code is aware of every individual tenant, just like the if and the switch statements. Your code knows about every tenant. And that's okay when your tenants are few or maybe a few dozen, but it's not okay if your tenants number in the thousands. You don't want to have to deploy a new version of your code when you add tenant number 1001. So if you're in that kind of world, you'd want to push your tenant-specific customizations into something outside of code. Maybe configuration files, maybe plugins, maybe webhooks, maybe something other and similar. The point is, though, that the customizations move outside of your code, so you can add tenants without making code changes and without having to make a new deployment. You could then even allow customers to do their own customizations. You could maybe have business support people helping them with that, but it's outside of your code. In our case, though, we know that our tenants are few rather than very many, so we don't need to go all the way to configuration, and we don't need that flexibility. So we stayed with the strategy pattern, and because we judged that that's going to be enough for us. Let's look at a strategy pattern. I'm sure you're all familiar with it, but here's just an example with the names replaced from our code. We have an SLA calculator, and an SLA is a service level agreement. The different operators have different expectations about how fast we need to deliver the replacement phone to you with your broken screen. So we need to adjust the calculation per operator, which means that we have an SLA calculator, which gets the current date and gets the date when the phone was sent and so on, calculates things around that, and then applies the tenant-specific strategy, of which we have two, one per tenant. So the question here is, how do you get the right ISLA strategy implementation? How do you provide it to this calculator? It turns out that if you use AutoFac for your dependency injection needs, there's a package called autofac.multi-tenant, which solved this for you. And it's literally the thing that this package was made for, literally the situation that it was written to support. And it's so easy to use. It's like you wave a magic wand and stuff just happens. This is a trimmed down version of our startup class from our API layer. And I've deleted everything that didn't have to do with the multi-tenancy bits. And what we have here is we configure a container with all the dependencies for our application. And that's the step where it says container equals. Next step, we tell AutoFac how do I identify tenants in our application. So we implement the tenant identification strategy. In our case, the API gets tenant information from the request header. So the tenant identification strategy does its job using the HTTP context from which it gets the request and then the header. And then you configure your multi-tenant container and register strategies per tenant. So first we configure tenant 1 and register for it tenant 1 SLA strategy. And then we configure tenant 2 and provide it with tenant 2 SLA strategy. And that's literally it. For each service of which you have tenant-specific implementations, you have 1 and 2, and you put them in the same container. And AutoFac.multitenant does the rest and always gives you the right implementation for the current tenant as specified in the request header. Unfortunately for us, this turned out to be a complete dead end. Again, we were like 90% done with our implementation, and then we hit those few special cases that brought this all crashing down. And the problem is, again, in our case, those third-party API requests, incoming API requests into our application. They come in without tenant ID because those third-party applications don't care about our tenancy solution. So the tenant identification strategy can't do its job. And because the tenant identification strategy is applied very early in the request pipeline, when the dependency injection container is built, there is no way to get around it. There is no way to override its decision. There's no way to tell it, oh, I don't have the request header for you now, but I can give you a tenant ID from a different place in just a few milliseconds. You can't do that. You can't defer the decision. You can't override the decision. You can't have, let me give this to you later. So in our case, this tiny piece of the application meant that all that nice magic was effectively useless for us, which is often the case with magic. When magic works, it's lovely. And when it doesn't work, you're helpless because you don't have access to the inner workings of that magic wand. So we had to throw out the magic wand and we had to do this ourselves, which actually wasn't that hard either. Our SLA calculator needed to get a little bit more logic in it. It could no longer just magically get the correct strategy. It has to instead explicitly get the current tenant and then use the current tenant to look up the correct SLA strategy with the help of an SLA strategy provider. Instead of having this magic container that just knows about tenants, we still have our two SLA strategy implementations, but we now more explicitly key them of tenants. So we register two instances and tag them or key them. This one is for tenant 1, this one is for tenant 2. And then we implement this little SLA strategy provider class, which gets a lookup index from the dependency injection container with all the registered strategies and just based on the tenant ID looks it up. So the I-index here is like a dictionary or a lookup list. So it's a bit more manual. It's a bit more code, but really not much. And yeah, solves the same problem without the magic and more flexibly, because here we can get current tenant from different places depending on whether we are in the normal web and API context where we have the tenant ID in the header, or we don't and we look it up later. And that was it. That takes us to the end of my story. With that, I've described to you the architecture that we chose, the thinking and the reasoning behind the architecture, and I've also showed you exactly the code that we used to implement this. This has now been in production, fully in production for about 6 months. And thus far, we haven't regretted any of our architecture choices. The architecture works out great for our needs. The code is working great, and we haven't had a single bug related to multi-tenancy, as in data leaking this way or that way, whether it's reading or writing. So that's what we have. And with that, I'll hand it back over to Madde and any questions that you may have collected during this presentation.
Thank you so much, Helen. And that was a really, really comprehensive presentation. Really good. And it did have a very happy ending, so that was nice. I actually did have a question. You kind of answered it, but I'll ask it anyway. So, in hindsight, now that you have all the answers to this problem, would you have made any different decisions? For example, with the database that you had and stuff like that.
Possibly we would have skipped the row-level security solution that we have in SQL Server because it affected performance so badly. We had not expected to have that much of an effect. We still kept it sort of part way there for the tables where we could manage it, but it gave us less value than we had hoped. And any of the other sort of wrong turns that we took, we already reversed as we were working, and now that it's in place, we're happy with what we have.
I guess they also provide good learning opportunities. Sometimes you need to do some wrong twists and turns to find the right solution.
Yes. I don't think we could have learned as much as we did if we just taken somebody's finished solution and applied it.
No. How did you handle, like if you did find out that you had to redo something, how did you manage your stakeholders? Did they ask like, why do you redo it? And I mean, did you have to handle that?
To some extent, the major course change from multi-instance to multi-tenants happened so early that our stakeholders weren't really very aware of the details. We just told them we're designing, and we sort of got that done within the scope of that design discussion. The auto-factored multi-tenancy magic, there we actually noticed it when we thought we were done and then realized almost in final testing that, hang on, this is not working in some scenarios. But luckily the code changes needed were so small that it didn't make a huge difference. It was maybe a day or two extra with testing and everything. So it wasn't a big deal.
Another question related to stakeholders. So how did you handle different stakeholders / tenants having different requirements on the system?
We, as much as we can, we try and minimize that. And we have a very understanding product owner who is very aware of development costs. So when our product owner talks to both the current operators and possible new tenants, she pushes back quite strongly when they come with requirements where they wish things to be customized for them, because she knows it costs development time. So we do as little as possible. And the parts that we do, well, the technical implementation is what I described here. It's mostly the strategy pattern and some switch cases here and there. But we're trying to keep it to a minimum where possible.
Another question. Am I right in presuming that every tenant has their own API instance and that all tenants share the same database?
They share everything. So they don't have separate instances of the API or anything. It's one web application, one API, and one database. So everything is shared.
And do you have auto scaling enabled for the API instances? For example, each tenant has, say, 3 to 10 instances.
No, we just have one instance. The amount of traffic we get is not huge because the number of people breaking their phones is not huge.
Really?
Surprisingly, we have between a few 100,000 claims in our database. So it's not like we have millions of people and they don't come here for fun. They create their claim and then they get their new phone and then they effectively leave us. So the amount of traffic is not huge. And it's quite stable and predictable. People break their phones at a sort of a reasonably constant pace. We don't get surges when something interesting happens in the world. So we're not affected by that kind of thing.
Okay. that was all the questions that we had. As I said, I found this session very interesting, and I really like the whole both getting the story behind it and getting the real code examples. That's just it's much easier to understand. So that was really good.
I'm glad you liked it.
And I haven't been able to stop thinking about your about your
brag.
2 truths and a lie, about your brags. But I decided that I don't think that you have met the King of Sweden. Am I right?
No, you are not right.
You have met him.
I have met the King of Sweden. Well, he probably doesn't remember me. It wasn't the kind of situation where we, shake hands and.
You didn't share a moment.
What happened was in my university days, our university student union got a new Swedish flag, and we got it very officially in a big ceremony with lots of other organizations also getting the Swedish flag. So we were like one in a queue of 20, I think, and I was one of the student representatives who received the flag of Sweden from the hands of the King of Sweden.
Wow, that's a really big flag ceremony.
Indeed. So my lie was actually kangaroo meat. I have never eaten kangaroo meat. And if I was offered, I would probably decline because I'm now a vegetarian.
There is actually a store here in Malmö that has like exotic meats. They have kangaroo meat and alligator meat, I think.
Yeah, they'll be
so if you ever come here, I know what I could cook you for dinner.
Fill out my brag list.
Exactly. Well, thank you once again so much for joining us here today. It's been great having you.
Thank you for having me.
And as I said in the beginning, we love to share knowledge with you, and we're delighted that you want to join us here. And we do have more sessions planned. So do you like machine learning? Because next Wednesday, we will be joined by Daniel Hinrichs, another colleague and a developer at 1337, and also the co-author of the book Xamarin Forms. And he will be here talking about building smarter apps with machine learning. So same time and same place next Wednesday. But until then, stay safe and take care. Bye-bye.